My name is Julius Cassis, and this is our Mission Design to Ceres. My team members include Logan Tomes, Sarah Ramlawi, Ricardo Gonzalez, Nick Nguyen, and Zurisadi Mehta. We are from California State Polytechnic University of Pomona, and we represent the Aerospace Engineering Department.
For this presentation, the outline will be mission overview, introduction, modeling assumptions, technical calculations and analysis, the final design, and a summary of our results. Followed by the summary, there's an appendix with the MATLAB codes associated with calculating the final results. For the Ceres mission, the mission goals are to design a round-trip mission to Ceres to retrieve scientific data samples, to minimize delta V of the mission, and to maximize delivered mass to ensure that we have enough propellant for the entire mission, perform a re-entry with velocity less than 10 kilometers per second to Earth's atmosphere, return at most 15 years after the launch date. To accomplish our mission goals, the major concepts used were the Lambert equation for direct trajectory, orbital insertion for parking orbit maneuvers, descent trajectory, and making sure we were in a sun-synchronous orbit.
These are the key results of the entire mission series. Starting with the delta V calculations, we have our first delta V burn, which is the insertion burn, to circularize the spacecraft. Once the spacecraft is circularized, we have a delta V land and delta V booster for the lander to land on the surface of Ceres. We then have a delta V launch and delta V rendezvous for the lander to launch and rendezvous with the spacecraft. Once the lander rendezvous with the spacecraft, it will begin a refueling session and orbit around Ceres for an optimal time to leave Ceres. Once there is an optimal time to leave Ceres, it will do a delta V return of 4.4758 kilometers per second. This is to minimize the propellant needed for the entire trip. The total propellant mass came out to be 5,210.4717 kilograms, and the total mass of the entire spacecraft with the propellant came out to be 6,410.5 kilograms. The Falcon Heavy Expendable can hold up to 6,475.8 kilograms of payload for our optimum C value. This means that the entire mass of the spacecraft can be launched using the Falcon Heavy Expendable rocket.
Ceres is a dwarf planet located within the main asteroid belt of our solar system. The mission is designed to collect data samples for scientific studies about this celestial body. For the software used, we use MATLAB, trajectory optimization tools. NASA's JPL Horizons website was used to obtain the ephemeris of each planet, and FreeFlyer was used to simulate the direct transfer trajectory. Technical calculations and analysis. For calculating the sun-synchronous orbit required orbital inclination, we first calculated the ascending node rate in equation 1. Then, with the ascending node rate, plugged it into equation 2 to find the required orbital inclination at 90.16 degrees. MATLAB was used to generate the Lambert equations using the given inputs: the velocity of Earth, the velocity of Ceres, position at Earth, and the position at Ceres. The ephemeris was then plugged into Lambert's equation, which then generated V1 and V2. V1 and V2 are the heliocentric velocities of the spacecraft using the following relationships. Equation 3, we were able to produce V infinity 1, and through equation 4, we have V infinity 2, where v infinity 2 is the velocity of entering Ceres' sphere of influence. Using equation 5, we are able to find the parking velocity at Ceres.
This chart shows the range of acceptable launch C3 for our given departure dates and arrival dates. This C3 must be less than 100 kilometers squared per second squared and greater than 40 kilometers squared per second squared. Shows the range of delivered mass for our given departure date and arrival date. We want to maximize delivered mass, and in order to do that, we need an optimal C3 value. This optimal C3 value was 41.1223 kilometers squared per second squared. This chart shows the range of acceptable delta V from Ceres to Earth for all hyperbolic entrance velocities less than 10 kilometers per second for our given departure dates and arrival dates.
The timeline for the overall mission includes Earth departure June 10, 2025, with arrival at Ceres September 3, 2026, and a departure date from Ceres August 12, 2033, and Earth arrival December 5, 2034.
Our final design for the launch vehicle was a Falcon Heavy expendable. This rocket was chosen using the data from NASA Launch Vehicle Performance website and a curve fit generated by MATLAB to give us our maximum mass delivered for our C3 value of 41 kilometers squared per second squared. Our spacecraft design included a HM7B engine that has an ISP of 446 seconds for maximum efficiency of propellant. The mass of this engine was 165 kilograms, which was beneath the dry weight of the spacecraft of 1,200 kilograms.
For descending and ascending on Ceres, we chose to land at 0 degrees longitude, 180 degrees latitude. The orbital period for the spacecraft is 8,167 seconds. For descending, the lander counters the orbital velocity at 0.34 kilometers per second. This brings the lander to 0, allowing it to free fall, and as it descends, once it reaches 45 kilometers, it counters its downward velocity of 0.155 kilometers per second. This allows the lander to land safely and give it 5 kilometers of a drop before hitting the ground. For ascending, the lander boosts at 0.164 kilometers a second after being on the surface for 8,020 seconds. Once the lander reaches 50 kilometers meeting with the spacecraft, a last burn of 0.34 kilometers per second occurs to match with the spacecraft's velocity. It takes 147 seconds for the lander to reach the rendezvous with the spacecraft. Therefore, the lander must begin ascending when the lander is 6.48 degrees relative to its normal. We have diagrams of a lander and a rover that we've designed, ensuring that we would get the samples that we needed from Ceres. The rover's main function is to roll off the lander, receive those samples, bring it back to the lander, and the lander ejects from the surface of Ceres, leaving the rover behind. Here we have a visual of the spacecraft and its heliocentric transfer trajectory as it leaves Earth on June 10, 2025, and rendezvous with Ceres September 3, 2026. Here we have a representation of the spacecraft orbiting Ceres 50 kilometers above the surface at 0.347 kilometers per second. this animation, we have the interplanetary spacecraft returning back to Earth on its heliocentric trajectory. February's data of Ceres and Earth for a time frame of 2025 to 2035 were inputted into Lambert equation to determine V infinity. The dates for each V infinity were compared using MATLAB to determine the launch and arrival dates that maximized mass delivered. The same method was used for the return trip, except the MATLAB code was used to determine launch and arrival dates that optimized delta V, which kept re-entry velocity under 10 kilometers per second. The samples from Ceres are collected using the rover, which is loaded onto the Ceres lander. Then the Ceres lander launches back to meet with the space vehicle.
Here is the compliance matrix showing our completion of each requirement. All requirements have been completed.
This portion of the appendix, we included the iterative solution for Lambert's problem, as well as the delta V's. In addition to that, we have the projectile drop, the rendezvous with spacecraft, calculating its period, and also calculating the inclination of the orbit.